Kia ora tātou. Welcome to this video where we'll be looking at how temperature affects the rate of a reaction. So there's a graph that you might remember from the structure and bonding part of the topic, where we would have on the y-axis is the energy, and on the x-axis is reaction progress. And we looked at like endothermic and exothermic reactions. So if we had the reactants here, then they would, if the reactants collided, there would be an activation energy, and then we end up going down here where the products have this amount of energy. And so this energy in between here is the energy that was released to the surroundings, so the change in enthalpy, and then this reaction here is the energy that's required by those particles to just react and become a product. So this was called the activation energy, which is shown by a capital E, and then in the subscript we write a capital A. So EA is the activation energy. So if we've got two particles here, let's call this section A, section B, and section C, going down here. So if they're moving relatively slowly, so there's a low temperature, so they have a low kinetic energy, so we can show that with EK. So this is proportional to the temperature, so low temperature. Then they might collide. So they're in section A at the moment, they're just moving around and they're colliding, but they're not colliding with enough energy to overcome this activation energy. So they'll go into B, and then they'll move back into section A and just be two reactant particles again. That's because they haven't had enough energy to overcome the activation barrier. If we were to move these particles around with a greater kinetic energy, so more temperature, then they would collide, and in this case, after their collision, they're now going to remain as products because their collision had enough energy to overcome that activation barrier. So that's the effect that temperature has on the rate of the reaction, is that more collisions, if we're increasing the temperature of a system, then we're increasing the kinetic energy that all of those particles have within that system, or within that beaker or whatever. And so when the particles collide, it's more likely that we're going to result in a product being formed. The other thing is that if the particles are moving around faster, then there are going to be more collisions per second. So if you can imagine, if we was to draw a little box here, and we had 10 particles inside, 4, 5, 6, 7, 8, 9, 10, if they were all moving around really, really slowly, then every now and then they would collide. But if they're moving around a lot faster in the same amount of time, we would get a lot more collisions. Relatively intuitive. So those are the two things that we need to include if we're writing an answer about temperature. One is that there will be more collisions with enough kinetic energy to overcome the activation barrier, and then there will be greater frequency of collisions. So this is slightly different to concentration and surface area, where concentration and surface area only increase the frequency of collisions, or the frequency of effective collisions. It's important to include the word effective, because if we're just increasing the frequency of collisions but none of them are effective, then we're not actually going to be increasing the rate of reaction. So this was surface area and concentration, and then we're now introducing this with temperature as well. So temperature affects both of those things. So let's look at a past exam question. So when oxalic acid solution reacts with purple acidified potassium permanganate, the purple colour fades and the reaction is complete when the mixture turns colourless. The picture shows the colour change after 45 seconds for 3 different temperatures. Explain how the rate of reaction for this experiment is affected by the temperature at which the reaction occurs. In your answer, refer to the information in the picture, collision theory and activation energy. So to answer this question, we can first of all just show our observation of what's going on. So at 20 degrees, the solution remains relatively purple, and then as we increase the temperature, the purple color has faded more after 45 seconds. So let's just say as the temp increases, the reaction has proceeded further. So as shown by the change in color. By the change in color. So let's explain how we know this by talking about collision theory and activation energy. So for this we will talk about when there is a higher temperature, is a higher temp, that is going to mean that we've got the increase in kinetic energy of the particles. So more collisions, so there will be a greater frequency of collisions. There's a greater frequency of collisions. And we could say this is because the particles are moving faster as well. And the next thing we would say is that the more collisions will have sufficient energy to overcome the activation energy. So more collisions have sufficient energy to overcome the activation energy. Let's have a look at what the model answer says. Get straight into it. So the warmer the solution, the more complete the reaction, the greater the color change after 45 seconds. An increase in temperature means an increase in the rate of reaction because the kinetic energy of the particles has increased. The particles are moving faster, increasing the frequency of collisions. So it's talking about kinetic energy here, saying that kinetic energy has increased, but then also saying that means that the particles are moving faster. More of these collisions will have enough energy to be successful collisions, which means their energy is greater than the activation energy. Overall, this leads to a greater frequency of effective collisions, so the rate of reaction is increased. So that's something that I hadn't quite included in our answer, but that's just to tie it all up. So we've got through temperature, surface area, and concentration now. Let's move on to catalysts in the next one.